Everyone, welcome back. Okay, so we have a whole lot going on here. We have car A, which is moving in a straight line up, while we have car B, which is going along a curve to the left. And what we want to figure out is, okay, what are their velocities? What is their relative velocity and what is their relative acceleration? What's the relative velocity and what is their relative acceleration? And this right here, this might be important. So don't forget that. Now with that in mind, just like always, I'm going to give you a few minutes to try this on your own. Go off, do math, do science, come back, maybe even drive your car a little bit just to really get a feel for the problem. And you come back and we'll do it together, okay? So 3, 2, 1, and we're off. We're off. Let's do it together right now. We got this. I'm excited. Okay, so first off, we have to set up what our coordinate system is going to be. I'm going to say x to the right, y is straight up. That looks good. And so velocity of b, we're going to have to break that up into components. We need to get the x component and the y component, x and y. Okay, so let's do that. So I got my guy right here. Here's my velocity. That's 30. And then I'm going to have this angle right there. Okay, so I draw my little right triangle. I know that this is 30 degrees and this would be 60 then, because that's 30 degrees. And now I'm going to have to name my side. So since I'm going to go from this 30-degree angle right here, this would be adjacent, this would be opposite. So for my x component, it will be opposite over hypotenuse, which is sine of 30. And it's going in the negative x direction. And for my y component, it will be adjacent over hypotenuse, which is cosine of 30, and that's going up, which is the positive y direction. And you see what I get right there. Now VA is just going straight up. It's just along the y-axis, so it's super simple. And then from that, we can calculate our relative velocity very, very simply. Oh, shouldn't have written so much right there. There we go. Very, very simple. We take our velocity of b in its Cartesian form, subtract the velocity a in its Cartesian form, and we get this. And if we want to, we can take the magnitude, which is just Pythagorean theorem, and if we take theta of the y component over the x component, we get the angle, which comes out to be 43.1 degrees. That's to the negative x-axis. Okay, now that all makes sense. That's all well and good. What about the acceleration? Because this one's going to round a curve right here. And so how is that going to mess us up? How's that going to change things? Well, look right here. Since car B is traveling along a curve, acceleration B is going to have multiple components. It's going to have a normal component and a tangential component. You can't forget that. Now you're probably confused, like, well, wait a minute, why is there so much stuff going on here? Well, let's break that down. What we're having to do is we're having to convert the components of our tangential and our normal velocity into components that are along the x and y axes, because they're not. So let's look at this section right here, because that is connected to my tangential component. Okay? That's connected to my tangential component. So you know that we have an acceleration, and that's the tangential acceleration because we're on along a curve. And that's going to be 3. And so what we do is we break it up into its x and y components, just like I did with velocity. I say right this like there, that right there. I know that this is 30 degrees. And I do exactly the same math as I did earlier, okay? Exactly the same math as I did earlier. And all is well. But now let's look at the normal component. So that's the one that's going to probably be the most confusing to people. The normal component. So, tangential right here, and my normal would be pointing right here. There we go. Now, first off, what is our normal acceleration? Well, AN is always going to be equal to v squared over rho, which is going to be 30 squared over 200 in this case. So that's why you see this 30 squared over 200. That is the acceleration, normal acceleration. And now we have to break it up into components. So when we're breaking things up into components, well, we gotta be very careful with our angles, and I always want to mess this up, so I'm gonna be very careful at this moment to make sure I don't mess anything up here. Okay, that should be a right angle. That's all good. Find a Danny. And if I do that, yes, that would be 60, and that should be 30. I believe I've got everything here. Okay, now I'm using the 30 degrees right here. And this is my normal acceleration, AN. Not gonna bother turning into this because that's just gonna be a pain. We're at 30 degrees right here. Now I want to first get the X component, which is going to be adjacent over hypotenuse. So it's going to be cosine of 30. And it's going in the negative direction. And I want my Y component, which is, it's going down here. Okay, that's good. And it is going to be opposite over hypotenuse, which is sine of 30. And it's negative because it's going down. So I broke up the tangential component and the normal component into their respective Cartesian forms. I know this looks very confusing, but all we did is we said we had a tangential and a normal component, and we took those individually and broke them up. And then of course we would add them together to get just nice little numbers. So with that, we can then pretty easily calculate our relative acceleration. If we look at that, our relative acceleration is then subtracting those two Cartesian vectors, which we can then take the magnitude of using Pythagorean theorem and get our angle for, which would be 74.8 degrees. So your relative acceleration and your relative velocity do not necessarily have the same angle or same direction. Don't forget that. That is important. Okay, so with that, we are done. We have completed this. So thank you for listening. I hope this helped you, and I will see you all next time. Bye-bye.